Hi, calculus students. My name is Amanda Olson, and I just wanted to take a little bit of time to give a brief introduction to limits. So what I'm going to do in this video is I'm going to discuss limits and kind of where they're used, and then we'll look at estimating a limit using numerical or graphical approach, and then we'll learn different ways that a limit can fail to exist. We will not in this section be looking at formal proofs of limits, and we won't be looking at an epsilon delta definition of a limit. So if you're kind of wanting something with a little bit more rigor, this would not be the video for you. Mostly this will just consist of kind of summary campfire talk without a lot of mathematical rigor. All right, let's get into it. So when we have a function, let's say this function here, we have f of x equals x to the third minus 1 over x minus 1. When we have a function like that, we know, of course, that this function is not defined when x equals 1. Okay, so if you were asked to find f of 1, we know that would end up being, 1 to the third minus 1. 1 to the third minus 1 over 1 minus 1, or 0 over 0 indeterminate form. So right away, we know we can't input 0 in, it's undefined. There's nothing more we can talk about it from an algebra standpoint. Calculus, though, we introduced this idea of limits, which says, okay, we know the function's not defined at x equals 1. But if we could put a point in there, what would be the point that we'd want? Is there a point that, we would ideally like the function to be to have as an output for x equals 1? And we kind of consider that. So I'll start off with looking at a graph of this function. So graphically, if you look at the function, and if you use a graphing software like Desmos or something else, you'll have to actually click and zoom in, because it'll look like, unless you really zoom in or unless you click on it, it'll look like this circle's closed, but it's actually an open circle if you zoom in, because of course we know it's not defined when x equals 1. However, if you consider the graph, you're going to see that it is defined everywhere as close as you want to get to the x value of 1, the function is going to be defined. So what that looks like is, if I look at x being, values to the left of 1, something like 0.99, 0.999, 0.99999, as close as you want to get to 1, any value to the left of it, slightly less than 1, you're going to have function outputs. And you can look at your function outputs and see, is there a pattern with those? As I get closer to 1 from the left, are my function outputs approaching some value? And then similarly, you can look to the right. So you can look at values just slightly above 1, something like 1.001, 1.0001. This table isn't exhaustive. You can get as close as you want to 1 from the right. And is there a pattern? And of course, this table is already pre-made, but you can definitely go ahead if you want. And if you don't trust it, or if you just feel better about it, you can create your own table. So put this into, you could make a table of values, and you can go through, put in different x values, look at the corresponding y values and things like that. You could use graphing software, you could use an Excel spreadsheet, any one of those kind of things to make a table of values and consider, what are the outputs. But hopefully you get some sort of table like this, and or a representation of a graph that looks like this graph. When you do that, you can see that there is a trend. So while the function is not defined for x equaling 1, I notice that as I have x values that get really close to 1, whether it be, values slightly less than 1 or slightly greater than 1, when it's slightly less than 1, we say, looking at it approaching from the left. When it's slightly greater than 1, we look at it, we say we're looking at it approaching x from the right. So hopefully when you look at values coming in from the left and values coming in from the right, you notice a pattern. And that pattern is that your function is getting, in this case, it's getting really close to an output of 3. Now, of course, we can't actually plug in 1, and we can't actually get 3 as an output. But if we could define this function, if I could, change this function in any way, I would probably change it so that I would have this value of x equaling 1 having an output of 3. Okay, because that's the trend. So limits, we recognize with limits that sometimes the function is not defined at a specific value. For this particular function, we're considering a limit as x approaches 1. And we recognize that the function is not defined at x equals 1, but we can talk about the limit at x equals 1. In other words, what's the trend? What would we expect it to equal? And what we would expect is that we would expect if it was defined, it would probably have an output of 3. So limits give you an idea of what would you expect, and they're not dependent on a function being defined at a given value. You don't have to look at a limit where a function's undefined. For this given function that I originally had, we could certainly talk about, what's happening, the limit as x approaches 2. It's not very interesting, but we can talk about it. What this would look like, the limit would just really be just f of 2, right? Like, because it's defined there, there's not really any surprises. Right, so we would plug it in and we would get 7 over 1 or 7. Nothing interesting there. So we can definitely talk about it, even if it's a place where the function's undefined. What we like to focus in on, though, is we like to talk about and use limits where, the function's not defined at a given value. So with functions up until this point, one of the first things you did when you talked about functions in your algebra classes, you looked at what's the domain of the function. In other words, where is the function defined? What values can I input into the function? What values can I not input? In calculus, we say, okay, there's places where we can't input x values, right? There's x values places, there's places where the function's undefined. Okay, the next best thing then is if the function's not defined at a given x value, what's the limit at that given x value? Does that limit exist? Now, your strongest case is where the function's defined at a given point and the limit and the function agree. Your next case is that you maybe don't have that the function's defined at a given x value, but the limit exists at that x value. Okay. So if there is a pattern or a trend for a function, and you can look at that tabularly or graphically, if there is a trend, then we say that the limit exists. Now, there's 2 different types of limits. There's a left and a right-sided limit. Okay, we say that the limit as x approaches a given value, in this case, we could say c, from the right, we put a little plus there. That just means from the right. So we read right to left, numbers increase from left to right. We read left to right and numbers increase from left to right. I think I misspoke there. And so if we're coming from the right, we're coming from larger values. So when we look at this tabularly, this would be the limit as x approaches 3, as x approaches 1 from the right of f of x. And of course, based on these table values, we can see what are the function outputs approaching. The function outputs are approaching 3. So we would say the limit as x approaches 1 from the right, that superscript of plus means from the right, of f of x equals 3. And we could look at that graphically and read that as well. Then the other notation is if I say the limit as x approaches 1 from the left of f of x. In this case, we can see as I approach from the left, that superscript of the minus on that 1 is saying x approaches 1 from the left. We would say that this also equals 3. So then we can make the conclusion, the left and the right-sided limits agree. So the limit as a whole exists. So the general limit exists. So this would be the limit as x approaches 1 of f of x equals 3. Okay, so if the left-sided limit and the right-sided limits agree that the limit as a whole exists. And that's what this is saying. This is kind of just outlining the notation. Now, sometimes it happens, where a limit might exist or it might not exist. If I was considering this example and I wanted to know, where does this limit, does it exist? Does it not exist? We'll look at some theorems later on about how to determine if a limit exists, but right now we're just going to focus on, table of values and graphically how to determine if a limit exists. There's also a way to do it algebraically, looking at limits algebraically. That tends to be the most efficient way, in my opinion, but definitely, we'll see other ways of looking at limits. So here, if I wanted to determine if this limit exists, I have this function, and what I like to do, first of all, is it defined at 0? Because if it's defined at 0, that's usually going to be the limit. So I might just check, what is f of 0? Well, this is going to be 0 over the square root of 0 plus 1 minus 1. This is going to be 0 over, 0 over 0. So it's not defined, but that's okay, right? Best case, the function's defined at a value. Okay, then we don't have to even consider limits. We've got the nice happy functions defined at a value. That's great. In this case, though, the function's not defined at this value. So we look at, that doesn't mean, it doesn't have a limit. So let's look at the limit. I will note the reason that I'm considering only for x equaling 0 is because that's what the problem asks us. We're not being asked to consider the limit as x approaches 2 of x over the square root of x plus 1 minus 1, although this might be a problem that you see in your homework. And I could definitely give you this and stuff like that. It's just that this particular problem, we're looking at 0. And yes, this was specifically chosen because, of course, 0 is the nice place where it's undefined. And so that's kind of the interesting place. But that doesn't mean, we have to exclude. You could look at x approaching 2 for this given function, and that's okay too. So then what we can do, since we saw the function's not defined at x equaling 0, is we could go ahead and graph or make a table of values for our function. So of course, this is using that function that we just saw. This is f of x equaling x over the square root of x plus 1 minus 1. And that's the function for which we said, it's not defined when x equals 0. So you can see then, so we plugged in these different values and we made a table of values. And so we chose some values that were slightly to the left of 0. So things like, negative 1/100th, negative 1/1000th, negative 1/10,000th, things like that. And then we looked at what are my function outputs approaching, and they happen to be approaching something. In fact, they happen to be approaching 2. So similarly, then we can pick some values to the right of 0, and we can look at what happens as we pick values that get closer and closer to 0, but they're still just slightly positive. So I have like 1/100th, 1/1000th, 1/10,000th, things like that. And I still see, though, there is this pattern of my function outputs. They're still continuing to approach a value, and that value is 2. So I would make, just with this table, I would make the conclusion then, because I have this right-sided limit, the limit as x approaches 2 from the right of f of x, that equals 2. And of course, I'm going to fix this. This should be approaches 0. And then I also have the case that the limit as x approaches 0 from the left of f of x also equals 2. Because the left-sided limit and the right-sided limit both agree, we can make the conclusion then that the general limit, the limit as x approaches 2 of f of x, I did it again, as x approaches 0 of f of x equals 2. Okay. So limits are y values, they're function values. But we consider limits at given x values. So we're looking at, where our function's undefined, what is the output? Or, it could be where a function is defined, it doesn't have to be where it's undefined. And then of course, if you wanted to, you could have graphed this as well. Sometimes people like graphing if you're more visual. A lot of times if you're graphing it by hand, you're going to make a table of values. So at that point, you probably would have both sets of data. But if you have computer software quick and handy, you may just graph this and kind of look at it. And like I said, for computer software, sometimes it might look like that hole is filled in. It's not necessarily, if you zoom in, it might not actually be filled in there. So just be kind of mindful of that too. So limits that fail to exist, because sometimes we have limits don't exist. So one type of situation where a limit might fail to exist is where maybe the right side of limit exists and the left side of limit exists, but they don't agree. So for this particular function, this is the absolute value of x over x, and we're looking at the limit as x equals 0. This is nicely graphed right here, and we can see the limit as x approaches 0 from the right of f of x. So what are my values approaching? They are approaching +1. Versus if I look at my limit as x approaches 0 from the left of f of x, these are approaching -1. Okay. These do not agree. Okay. So unfortunately, we get a contradiction. So the limit as a whole does not exist. That's one, situation that you can encounter. So other types of behavior that you might see, as some of these we're going to address kind of more later on in chapter 3, but you could see that maybe a function isn't just kind of stopping where there's not just like one point, but maybe it's increasing without bounds. So you will encounter some where you might have that your function oscillates. So some trig functions oscillate, and you could have a situation where your function is oscillating. That's also a situation where a limit might fail to exist. All right, so hopefully this gives you enough to try some problems. Definitely check out some of the homework examples and also reach out to me for more examples. Thank you.